Okay, welcome back everyone. In this session, we're just going to do some practice applying what we learned last time. So we're going to be looking at how to use Fnet equals ma and torque net equals I alpha to apply that to systems. So our essential questions are, how do we analyze the motion of an object that rotates and translates? And then we'll also talk a little bit about the concept of equilibrium. Okay, so first we want to derive an expression for the acceleration of a flat disk of mass m and radius r that rolls without slipping down a ramp of angle theta. Now this is something that we can do using conservation of energy as well as forces and torques. So we want to focus on forces and torques, at least for right now, and then we can go back. So here's our flat disk, and because it's a disk, we know that I is equal to 1/2 mr squared. It's just another one that you can look up. Okay? And we can think about the forces that are acting on this disk. And so we're going to have the force of gravity straight down. We'll have a normal force going like this. And then we're going to have friction. And the question is, which way does friction point? Well, here's the thing. If this is rolling down the ramp so that a point on the surface kind of goes then how does that work? What causes a torque to rotate it? Well, it can't be gravity. So the torque from gravity is equal to 0 because look at where gravity acts. It acts at the center of mass of the object, so R is equal to 0. Okay? Well, what about the normal force? Well, torque from the normal force is also 0 because think about the angle. Okay? Yeah, R is going this way, but F is going this way. So theta is 180. So the torque from that is 0. So then we really have no other option. And the only thing that we can say is that we must have a frictional force which points up the incline, and that will cause a torque from friction equal to the force of friction times the radius r. And they're at right angles. Okay? And we're going to pick the angular acceleration to be positive in the clockwise direction, okay, and that will make everything consistent and allow us to accelerate down the ramp. So typically when you solve these kinds of problems, you want to set up two equations. Fnet equals ma and torque net equals I alpha. Now Fnet equals ma, we think about our angle of ramp here, theta, and theta right here. So we have mg sine theta minus friction is equal to ma. And so we don't know what friction is yet, but we're going to solve that with torque net. The net torque is coming from friction, so it's just F times R. I is 1/2 mr squared, and alpha is a over r. So those can cancel, and friction is equal to 1/2 ma, which can be plugged into here. Okay, so we have mg sine theta minus 1/2 ma is equal to ma. Well, the m's are going to cancel, and we're going to get g sine theta is equal to 3/2 a, or in other words, a is equal to 2/3 g sine theta. Okay, now let's look at this result carefully. First of all, if it wasn't rolling, if it was just sliding down and there was no friction at all, it would be g sine theta. But the fact that there is friction is going to take away a little bit from the acceleration, but that's also what allows it to roll. So this is a result that is reasonable, and it has the correct units of meters per second squared. Okay. So now, let's try to calculate the initial angular acceleration of this rod of mass m and length L, and let's calculate the linear acceleration of the end of the rod. Okay, so first of all, let's draw forces. And really, we only have two forces. We have the force of gravity acting smack dab in the middle, but we're going to assume that this thing is pivoted or attached to a wall or something so that it's able to rotate in the first place, and we'll call that some sort of a normal force. Okay? So now what we do is we set up our two equations, and it's going to be rotating this way, so that'll be the positive angular acceleration, and we think that all the pieces will be accelerating down, which sort of fits with that. So first of all, the net force will be equal to ma, and the net torque will be equal to I alpha. Okay, so the net force is actually going to be mg minus F normal is equal to ma. Okay? But we're going to have to come back to that. We don't have quite enough information just yet. We don't know the normal force. Okay? So let's go and let's find the net torque. So if we say that the axis of rotation is this point right here where the normal force is acting, there's no torque from the normal force. It's equal to 0. So we just have the torque from gravity equal to I alpha. Okay? So the torque from gravity is going to be mg, and then if it's a length of L, it's actually acting at L over 2, right? Okay, so that's the torque, and then what we do is we look up the moment of inertia for a rod at one end, which is 1/12 ml squared. You can look that up. And we can therefore find alpha. So our m's cancel, l's cancel, that turns into a 6. So this means that alpha is basically equal to 6g over L. Okay. Oh, I'm sorry. I used the wrong number. That was for the center of mass. I thought something was weird. It's actually 1/3. Okay, so we have 1/3 ml squared. My apologies. So that doesn't cancel out at all. And actually what we get is 3/2 g over L, because don't forget about that L right there. Okay, does that make sense as an angular acceleration? Well, it's meters per second squared over meters, so yes. Okay, so now how do we get from this to the acceleration of the end of the rod? Well, we have the equation that A is equal to alpha times R. And in this case, R is L. Okay, so we plug that in. Oops. Whoops. Sorry, guys. This PowerPoint is not cooperating with me. Hold on a second, and I'll get right back. Okay, sorry about that. So we're back, and we just want to plug in alpha is 3/2 g over L, and then R at the end of the rod is actually just going to be L. So that's going to give us an acceleration of 3/2 g, which is kind of crazy. How can it be that the end of the rod has an acceleration that's equal to 3/2 g? Well, one way to put this into perspective is that the left side of the rod has an acceleration which is 0, because R is 0 at that point. So this is A for the right end. Okay, so A for the left end is equal to alpha times 0. And you could also say that A for the center of mass of the rod is going to be a half of that, or 3/4 g. Now that makes sense because we wouldn't expect the center of mass of the rod to be accelerating greater than g because there's no other forces going downwards. But you can think of it this way, that if it's rotating, the right end of the rod has to like sweep down a long distance to catch up with the middle of the rod that's not going as far. So it needs to have more acceleration for this to happen. Okay, let's try one more example. So in this example, now we have one of our famous problems from earlier in the year with pulleys and Newton's second law, but now this pulley does not have zero mass. It can't be ignored any longer. So we're going to assume that it has mass m, radius r, and it's a uniform disk, and we want to calculate the acceleration. So we're going to set this up by drawing forces, and we're going to call this T2, and this is going to be T1, and then m1 times g. And we're going to assume that friction is not a factor. Okay, so this means that actually the pulley has T2 going one way and T1 going the other. Okay, so you can't assume that the pulley is massless anymore, and so T1 and T2 are going to be different. Okay, so for M2, we can say that F net is equal to MA, so T2 is equal to M2 times A. Now A will be the same for all of these. Okay, and for M1, we can say again that F net is equal to MA, so M1G minus T1 is equal to M1A. And then for the pulley, well, let's just look at that in a little bit more detail. So this T1 is going to be causing a negative torque, and this T2 is going to be causing a positive torque. Okay, but because everything is accelerating downwards, T1 is actually in the positive direction. So we have that the net torque on the pulley is equal to I alpha. And the torque is going to be T1R minus T2R. And that's equal to I, which for a pulley is 1/2 mr squared. And alpha is A over R. So these are things that we want to memorize, such as alpha being A over R. So one factor of R will cancel this way, and the other one cancels like this. And so we have T1 minus T2 equals 1/2 MA. And then we have three equations, right here, and right here. And our three unknowns are T1, T2, and acceleration. Now if we're going for the acceleration to begin with, then what we want to do is to add these three together. And you're going to see that on the left side, we are going to have some cancellation. Okay, T1 is going to cancel with this one, T2 will cancel with that one. So the only thing that we'll be left with is M1 times G, and on the right side, we're going to have M1 plus M2 plus 1/2 big M times A. And this means that the acceleration will be M1G divided by the total mass of the system. This is kind of cool because this is yet another example of the net force on the system, which is M1G, divided by the total mass of the system. I'll label that M total. It's not the same thing as big M. Okay, so next time we're going to do one more example problem, and then we'll be talking about work and power in rotating systems.